Hello friends, welcome to my channel. Let's have a look at problem 491 again, non-decreasing subsequences. In this video, we're going to give a treatment for this problem using a backtracking technique. This is a follow-up video actually. In a previous video, we explained how to solve this problem using bit mask technique. And in this video here, we're going to explain the backtracking approach to this problem. First, let's read through the problem statement again, and then we do the analysis and share the codes. First, the problem statement. So here, given an integer array called nums, we are required to return all the different possible non-decreasing subsequences of the given array with at least 2 elements. We may return the answer in any order. So here, the main requirements are the following. Find all different such subsequences. So here, subsequences, this is one point. Such means that the subsequences are non-decreasing and their lengths are at least 2. So with that said, let's look at the 2 examples. So in example 2, so here the output is a list consisting of one list. So here is a 4, 4, right? So the length is 2. So in example 1, so these are the lists that are non-decreasing. So in this problem, actually we need to also pay attention to deduplication. For example, if we choose the element of 4, and then we choose the third element, it's a 4, 7. So this is the one non-decreasing subsequence which is valid. So if we choose the first element and the fourth element, it also gives us a 4, 7. So we need to avoid this kind of duplication. So with that said, let's also examine the constraints or additional assumptions. So the first one will play a certain role in our solution. That is the size or the length of the list. So this length is bounded above by 15. So 15 actually is not a very large number. So if we consider all the possible sequences, including empty ones, so there are 2 to the power 15 possibilities, right? So the second constraint is on the range of elements in the given list. So the elements are actually bounded above by 100 in absolute value. So in other words, it's running between -100 and +100. So with that said, let's look at the method here. So in this video, as we mentioned, we're going to explain the backtracking method or technique. So this is actually a very routine or standard technique. So with backtracking here, we are going to build all the valid subsequences essentially. So here we will write a backtracking hyperfunction in recursion format to serve us as a builder or worker. And in the process, actually it's important to track the state transition and check the 2 conditions subject to this problem requirement. There are first, the length should be greater than 1, and secondly, the subsequence should be non-decreasing. So in here, we're going to share 2 slightly different formats of solutions. So though the solutions are essentially the same, so the 2 slightly different formats serve to present 2 different tricks to avoid duplication. So one is with the help of the set abstract data type, and the other is with condition check in the hyperfunction itself. So with that done, let's look at the first solution format. So first, I'm going to initialize a result variable. So for this, because we want to avoid duplication, here I'm going to use a set. So set will consist of unique elements, right? So this is the first one. And next, we're going to write a hyperfunction. So the backtracking function, hyperfunction. So for this, we're going to write with recursion. So here, let me define this. We're going to use backtracking. So here, we're going to track the index. So the index of this in this nums, and also we're going to pass a subsequence. So here, what we are going to pass to this argument is a list. So notice that list is mutable. This is actually an important thing because it's mutable, so we can make state transitions. So for convenience, I'm also going to introduce this n. N will be the length of this nums list, right? So with that said, let me first write some stop conditions and base cases. First, as long as the list has at least 2 elements and it's non-decreasing, then we're going to add it to the result. So for this, we're going to check if length of subsequence is greater than 1, which is equivalent to C is greater than or equal to 2. If this is the case, so we're going to append this subsequence to the set. So notice that set will store things that are hashable. So we're going to use immutable tuple. So we're going to use tuple. So it's immutable, right? So subsequence. So this is the one. And another thing is that if we are out of boundary, so then in other words, this I equals n or I greater than I is strictly larger than the last index n minus 1, then we're going to stop. So in other words, if I equals n, right, we're going to return. So this is a stop condition, right? You can regard that. And then we're going to check the non-decreasing condition, right? And then we're going to check if we can consider adding the current number nums I or not. So this is actually very standard. So now let's look at this. If not subsequence. So in this case, so we're going to at the very beginning. So the subsequence is empty. So nums I will be the first element if we add to the current subsequence. If not, this one or nums I, so is no less than the last element in the subsequence. So in this case, we could consider append the original, the previous state of the subsequence with the current number. So this actually corresponds to doing this subsequence append nums I, and then we're going to continue to the backtracking. So then we're going to go next state, then with the current state of subsequence. So as we mentioned that as a list, subsequence is mutable. And then after this, so we need to restore to the previous state. So we're going to do subsequence pop. So this actually finishes this condition. So if we do not do the check, actually it corresponds to ignore the current nums I. Then it corresponds to do backtracking from the previous state like this directly. So this will be the full format of the backtracking function. So as we mentioned, so we can think of this backtracking function as a builder or worker for us. So that's it finds valid subsequence. It's going to add it to the result, right? So here, let me change this one. So because we are using result, so it's not a list, so we are going to use the add method. So with that said, so we are ready to call the function, call the hyperfunction, right, and prepare the return. So we're going to call this function. So we're going to start from 0 and then with an empty list, and then we're going to return the result. So this way of returning the result is not completely confined with the return requirement, but it passes all the cases. So if you like, you can actually use a list compression to transform it to a genuine list. Anyway, let me first do a test. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes the generic cases. First, let me make this comment. Let me do the list for atom in a result. So this way, we'll actually return this format. So now let's first do a check. Atom. So here, list atom for atom in. Now let's do a check. Yeah, it passes all the cases. So this is one comment. So another comment is that here we can actually make a shortcut for this 3 line of code. So let me comment this out. So I'm going to replace this by from I+1, and then when we pass this argument, so we're going to do the append operation here. So we're going to use this plus this nums I. So this way it also changes the state of this subsequence, and then we do not need to do append and then do the pop, because we do this because the subsequent state does not change, right? And then we can directly call this this function. So now let's also do a check. Yeah, it passes all the cases. So this is actually a solution format corresponding to backtracking. So let me mark this as let me first copy this function signature, and then I'm going to change this one to be a method v1. And now let's look at another solution. So here a comment is that, so in order to avoid duplication, so here we are using a set abstract data type. So as we mentioned, so we're also going to write another format. So we're going to add a filter or condition check in the backtracking function, so that we can automatically avoid duplication when we're building the subsequences. So let me write this one here. So first I'm going to initialize our result variable, and then we are going to regard this one, each one as a pass, and then we write the backtracking function. So here what we're going to pass is the nums, still the list itself, and then start index. So here this start index corresponds to I, and this pass corresponds to the subsequence in the above solution format v1. And then first I'm going to check if the length of the path is greater than 1. So if so, what we're going to do is that we're going to append this path. We're going to pass a copy of it to the result. Then we're going to alter this state. And then we're going to do an iteration. So for I in range start index, and then the length of this nums. So here, if we can write length of nums, or we can, as above, we can introduce this variable m. So first I'm going to check a stop condition, or if path and path -1, the last element, is larger than the current number we are considering to add to the path, then we continue. So this is one case. Another case is that, so we also want to avoid duplication. For example, in this example, if we have scene 7 and we see 7 again, so in this case, if we need to avoid this situation. So this corresponds to check if I is larger than the start index, and so also we know nums I is already appearing in before, so it's nums start index I. In other words, we have added one. So we're going to continue. So this will help us avoid repetition. So next, so it's going to be the standard backtracking pattern, we'll see. So we're going to append this current number, nums I. And then what we're going to do is to do backtracking for nums, but it's start from I plus 1. And after we do this, so we're going to do pop, right? And then this is the main function. So next, what we're going to do is actually the same. So we're going to, let me make some annotation. So this is the backtracking hyperfunction with duplication. And then we're going to make function calls, and prepare the return. So due to the way we actually append the result to the path to the result, it's actually already the correct format, right? So that's not very essential for this problem, because here in the first one we can directly return the result variable, so though it actually consists of tuples. So here, let me first call this backtracking function. So nums, so from index 0, and then we're going to return result. So this is the second solution format. So before we make a comment, let's first do a check. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the test cases. So with that said, let's quickly summarize the two solution formats. So the two solution formats are based on backtracking, but the difference lies in the way we treat deduplication. In the first version, we are using a set abstract data type, and in the second version, we are using a condition check. So in essence, they are actually the same solution idea. So with that said, I guess that's about it for this specific problem and this follow-up video. You are welcome to check out other videos in my playlist and in my channel. Thank you.